Welcome to the Cosmic Pie Podcast, episode number 30. I'm your host, Wayne Barkhouse, and as always, I am with
Robert Moore. Nice to meet y'all.
So, Robert, we are broadcasting live from the campus of the University of North Dakota here in Grand Forks.
Or at least 2/3 of us are.
Right. We have a very special guest today. Our very special guest is Dr. Omar Lopez-Cruz, who's coming to us all the way from Mexico. Now, Omar, before you introduce yourself properly, I'm going to let viewers know that you have a nice tie-in with the University of North Dakota. You were the chair in astrophysics, the Oliver Benedictson Endowed Chair in Astrophysics in 2015 to 2016. And once in a while, I catch you wearing the UND hat.
Yes. Yes. No, I thank you, Wayne. And it was thanks to your intervention that I got that appointment and then your invitation. And my family and I had a great time along with your family too, meeting, the great north of the United States and being at temperatures of minus 33 Celsius for the first time for some members of my family. So it was great to do science at the University of North Dakota, at the Department of Physics and Astrophysics. And it was a huge experience for all of us, Wayne. We enjoy really a lot being there. I also attended some English classes, and I enjoyed it utterly with Professor Crystal Alberts from the Department of English. It was great. It was a great experience, very enriching for myself and my family.
Excellent.
So, Omar, did you want to sort of give a layout a little bit about what you do, where you are, the position you hold, and maybe then go on into some interesting things that you do research in?
Yes, thank you, Wayne. And that was the idea. I came with no plans, as usual. But I'm an astronomer, an astrophysicist.
Uh-oh. Uh-oh. We've lost him. Oh, no.
So we'll just wait. We'll try to reconnect with Omar here in a second.
Yeah, we're trying to reconnect with him. I don't know which end it was spat on, but I can't see anything wrong here.
We'll see if he reconnects.
Yeah.
He could be still talking, he still thinks he's on live.
I hope that he can either hear us or something.
Well, we'll see. So we got to wait, see if he can try dialing in again. Then.
Yeah. He just dropped off.
Okay, so he'll know. So we'll get Omar back. But, Robert, as always, there's been lots of things going on in space and in astronomy. And so just kind of fill in the time here. So one of the things I noticed that's happened recently is there been a real cool observation done of the atmosphere of an exoplanet.
Yep.
So if you want to bring up that slide, maybe we'll talk a little bit about this while we wait for Omar to come back. So the exoplanet is K2-18b. So it actually orbits the star that's about 120 light years away in the constellation Leo. Now, the estimated mass of this planet is about 8.6 times the Earth's mass, and its size is about 2.6 times the Earth's size. So that you're talking about a larger planet than our own Earth.
Right.
So that's the one thing to think about. And what you see is actually observations. It's the spectrum of light passing through the atmosphere of this exoplanet taken with the James Webb Space Telescope. And you'll notice that there are molecules that are labeled on this diagram. For example, we have carbon dioxide. We have a very interesting molecule. Do you want to see that starts with D? Notice that.
Ooh, dimethyl sulfide.
Yeah, and you know where that comes from on Earth? We have that, but you know what predominantly the source is on Earth of that molecule?
Usually bacterial action.
Life.
Yeah.
Life. So that makes you wonder and speculate, of course, is that what we have happening here?
Yep.
Very interesting result in that sense.
And I think we may be getting Omar back.
Hi, back. Sorry. Can you hear me now?
We can hear you.
All right. Thank you. So I said I came from the classical end of astronomy, and I'm very happy that I have done most of the 20th century astronomy during my career. And classifying stars and variable stars took me to Toronto. And I worked under Bob Garrison, who was a student of Morgan. And Morgan was a student of Struve. And it was a big generation of all of these very
I
important astronomers who gave the foundation to classical astronomy.
I
But
I, I hate to
uh-huh,
interrupt, but we still
uh-huh.
can't see you, Omar.
You had to,
Oh, okay. Yeah, you can see me now. Sorry.
We saw you there for a
There
second.
you
Now
are.
we can see you.
okay.
Excellent.
So I was very happy to be in Toronto, but I arrived in '89, and when I arrived in '89, there was CIRA, the Canadian Institute for Theoretical Astrophysics, and I was on a Mexican overseas scholarship. It was Mexico, we have mentioned already when we were preparing for the program that in Mexico, education is free, is public all the way. So Mexico paid for my fees and everything to attend the University of Toronto. And I was very happy for that. But when I arrived there, I look around and I ask, what is the best thing that Toronto is doing at the moment? And they said cosmology. And
Uh-oh. Ah, we weren't having problems with this earlier, folks.
Okay, so it looks like we're frozen for a minute here.
Yeah,
We'll see if he comes back or not.
I am so sorry, folks.
So getting back to what we were talking about with the exoplanet
Yeah.
atmosphere. So that's really interesting.
Okay.
Oh, he's back.
Okay, there we go.
Now we see you.
Now we can see you. I don't know. Oh, okay. I can see this nice little red set of bars on the Zoom link. So apparently it's Zoom having a problem. And apparently we've lost him again. Oh, Lordy.
Well, we can try it.
I will apologize, folks. We thought we had all the kinks worked out of this.
This is an internet thing, so it's nothing we can
It's nothing we can really
we can
do
do
anything
on our
about.
side. Okay, so we can talk more about the
Yeah.
atmosphere stuff a little bit here. So that molecule that we mentioned, the dimethyl sulfite, that normally comes from life, bacteria, as you mentioned here on the Earth. But that is not, the only source.
It's
You have
not
to-
the only source.
So we have to be
Right.
careful of that. So it could be the processes, the naturally occurring processes on this exoplanet that's producing that molecule that allows you to be able to see here in this type of observation. Now, the other thing to note here is that you really can't see the hydrogen and you can't see ammonia. So given the mass and size constraints and what you can see in the spectrum of this exoplanet from its atmosphere, chances are, at least the speculation is, that this is a water type of planet, which is interesting. So it would have large oceans on its surface. So
Right.
in some sense, we don't need to speculate. You can look at the spectrum and, given the constraints of the physical properties of this object, be able to say that. So it just kind of show you now what is some of the observations that we're getting now from the James Webb Space Telescope, and the future on this is very promising.
And it's only going to get better.
Yes.
And we've got Omar back, so we're going to try
Okay.
one more time
Awesome.
at least.
Okay, sorry, the connection isn't stable. I'm in a restaurant here. I thought the connection was right. But as I said, I have to, in less than 2 years, change my frame of thinking in getting into cosmology. And it was, you remember when Simon Lilly there teaching the cosmology courses. And Simon Lilly came from all the way from Hawaii. He was a British professor, very famous, very conceited, but he was teaching cosmology. And so I learned cosmology. It took me, blood and tears to learn cosmology. And then when it was the time to switching into a PhD, so I thought that, cosmology was too far. So I should do something like in the middle, which is extragalactic, just get outside our galaxy and study other galaxies. And for that, and that's what Wayne and I have in common, we choose one of the toughest supervisors in Toronto. Of course, when Wayne came, he was already tame. I had survived him. So Howard Yee was a professor that had come only recently to Toronto in '89, and he came around '90. So I went and talked to him and said, I want to do extragalactic astronomy. And he looked at me. He's a Chinese guy from Canada who studied Caltech, and he was recognized as the toughest guy. And so he looked at me and said, I think so. So I went to my committee and said, I want to work with Howard. And everybody, opened wide eyes and said, why do you want to work with Howard? You want to, commit suicide or something? Even the dean of the department came to see me.
Omar?
Said, Omar, are you proud? Yes.
Omar, I hate to interrupt you, but I will. By the way, people, whatever we say is our own personal opinion and not necessarily the opinion of the University of North Dakota, nor our department, nor our college.
That's good. I don't blame you, Wayne.
Okay, continue.
Gotta get that in there.
Yeah, no, that doesn't have to do anything to do with the University of North Dakota. No, this is Toronto. It's my opinion.
Right.
I mean, we love Howard, right?
Yes.
I mean, it's in our own way. I mean, he taught us a lot.
Yes.
A tough guy, a hardworking guy. I mean, like, who would come at 11 a.m. and leave like 9 p.m. every day. Every day, Howard would be there, but Saturdays. And I would not leave, and you would not leave before he did leave the department.
Yeah. And he was there every Sunday, too. Saturday was his day to do his wash and his grocery shopping.
Really,
Oh,
internet.
we're gone again? Okay. Yeah, so Omar is talking about our experience at the University of Toronto when I entered graduate school. It'll be the fall of '96. Omar was just finishing up when I arrived, so there was some overlap, which was great because it gave me a chance to meet Omar.
Right.
And he is a great guy, and we've stayed in contact over these years, published papers together, and so on, did various projects. I was fortunate enough to be able to go to Mexico on three separate occasions.
Okay.
And my first time, I forget which year it was, I was still a graduate student at Toronto. We went for a whole month during, I think it was the month of July, essentially, at Omar's Institute just outside of Puebla. And for those of you who don't know, Puebla's famous. You think of Cinco de Mayo, so it was the Mexican force against the French.
Right.
And there's the Battle of Puebla. So that happened in where Omar is actually located. So that's where the history behind that
Here
is.
he's trying to come back.
Okay.
So.
I came back. I'm sorry.
That's okay.
Stuff happens.
No, I'm saying things that I shouldn't say, perhaps.
Well, it's your personal opinion, so it's okay. As long as people know it's not sanctioned by the university or something, right?
Right. I mean, but Wayne, remember that time in Toronto when Nick Kaiser was there,
Right.
and also Peter Martin. I mean, those four guys
And
changed the face of Canadian astronomy.
Yeah.
I mean, you can correct me if I'm wrong.
well, unfortunately, Nick Kaiser just passed away not that long ago.
I know. It
Yeah.
was sad because he's still a young guy. There is a mystery around Nick Kaiser. In the time when I met him, in the 90s, Nick Kaiser was writing papers left and right and great ideas all the time. He invented, single-handedly, weak lensing. Many other people claim that they invented weak lensing, which is, the signal from clusters of galaxies on the background galaxies. You can measure the distortions. And it was all Nick's idea. I remember him actually getting very excited about the idea. And it was this guy, Gordon Squires, his student, that worked together, the whole formalism. But it was Nick's idea. I'm very sure of that. I saw it developing in real time. And of course, Nick was, a great guy. And then he left Toronto, went to Hawaii, and basically disappeared. You didn't see that many papers. He got this thing called this set of telescopes that are in Hawaii, when
Pan-stars.
Pan-stars.
Yeah.
With new ideas. It was Nick's, and actually, I mean, this is my own opinion. I have to clarify, Wayne. I think he left Canada because they didn't allow him to use CFHT to apply weak lensing. I think that's one of the main drivers that took him away from Toronto, because he was having a great time in Toronto. And those guys like Dick Bond, we became great friends because he was there in the middle of the night working at his office. And I would go down 2 floors down, and I'll go and interrupt Dick, and I would say, I don't understand the expansion of the universe. No, no, something more complicated than that. And he will try to explain to me, but he was such a smart guy that he had to, make a big effort to explain to a guy who was trying to become a cosmologist, coming from Mexico with not the proper background.
Right.
But I survived, and they were the same as you did, Wayne. I mean, we survived.
So Omar, when you were still in Mexico, was there any astronomy that you were taught then?
Yes, we was all classical astronomy, Wayne. I was with observers of variable stars, and here in Tonantzintla, where I work. And it was mostly classical things. If we mentioned the things that Hawking or Penrose were doing, they would look at us and say, no, you are out of your mind. This is too much or something. But we look at it, that it was something like a very far thing that only the theoreticians would do. And look at us, Wayne, nowadays. When in the times in the 90s, like a redshift of a half, like as Simon Lilly would say, it was high redshift. And now in my time, I have seen galaxies at redshift 3, and I'm looking for galaxies at redshift 20. And that's, is a different ballgame now. But at that time, it was, something, the frontier, we were pushing the frontier at that time.
And I'm going to mention something here. The redshift season mentioning is a number about how far the distance it is away. It's the Z number, as it's called, is a measure of that distance. So I forget, though, how it's arrived at.
Well, it's nonlinear, but the greater the redshift value, the further away an object is that you're measuring the light coming from that object.
Right.
Now, Omar, to me, you are the most famous Mexican astronomer that I know. And I think,
thank you, Wayne.
And that was a compliment. And to most people, I think you are the most famous astronomer in Mexico. But when you were, let's say when you're in high school or even in middle school, maybe, there's another astronomer from Mexico that I remember, and that goes with her big Harrow object. So do you want to say a little bit about that?
Oh yes, of course. That is Guillermo Haro. Haro, we'd say in English. Yeah. Guillermo Haro is the founder of my institute here in Mexico. In 1942, we got a Schmidt camera, which was the second largest in the world. It was designed in Harvard University by a guy whose name was Dimitrov, a great optician. And that was we mentioned wars at the beginning, behind the cameras. But remember 1942, Wayne. 1942, we were at war, right?
Right.
And this time the Americans pay attention to us because in the previous war, the Germans came and said to us, the Mexicans, that if we join them, they will help us to recover the territory that we lost to the Americans in the 19th century. And that almost worked. So this time, this time, they said, oh, the Mexicans, maybe the Germans will try to lure them back again. And so they moved faster. And they, strengthened these ties of cooperation. And we got the largest telescope, the second largest telescope in the world in 1942. 5 years later, in 1947, it was already working. And during those years, exploring the equator, the celestial equator. We have, because we are in the tropics, right? And we are at high altitude. We are over 2,000 meters above sea level. So it's not totally hot and you don't see all the jungle here. We are at the mountains, right? So we had access to regions of the sky that nobody else could cover from Europe or from the south, neither in Africa or South America. And if Hawaii wasn't developed yet. And then Guillermo Haro discovered these objects, and they called it his attention using a prism, objective prism on the Schmidt camera. And this is very different from what we do now. When you have a prism in the entrance of the telescope, imagine the prism there, and then getting all the spectra of the objects, and he discovered these objects. And Guillermo Haro was a lawyer by training.
Oh,
And he
wow.
became he became a greatest astronomer thanks to Barkhouse, who was at Harvard at the time and taught him how to observe. So he got the first grade training in observational astronomy and developed many techniques using the Schmidt camera that allowed him to do lots of discoveries. That is the Herwig Haro objects, because he didn't know what they were, and they sent the pictures, or the plates, to Minkowski, an astronomer in Carnegie Observatories in Pasadena, and that's why he got credited for, because he discovered them first. But he was about this close that the Herwig Haro objects would be just called Herwig objects, and it was thanks to the support of the American astronomers that they are called now HH, Herwig and Haro. And also they discovered a lot of quasars here, Wayne. And one of them is holds the record for having the largest black hole. But that is around redshift 3 or something like that.
Yeah.
So the tie-in, let's say, with the interest in the Herwig Haro objects, so that would show up as the mission lines, if I remember right.
Yes.
And so,
The nebula.
right, and so the tie-in with star formation, of course, you can think of the Bach globules as a tie-in there. So he had natural training in the whole stellar formation aspect of things,
Of course,
right?
yes.
Yeah.
And flare and dark and all those things. So what it was discovered later, either the Herwig Haro objects is just the shock, or the region where the jets from forming stars are carving to the interstellar medium, and then that is the place where they are shocking. And then you see this. And then it was also many Mexican astronomers, more famous than myself, Wayne, who actually discovered. There is Luis Felipe Rodriguez. He's the biggest Mexican astronomer, the foremost. And he, using the VLA, and got to explain what the Herwig Haro objects were. I mean, they were discovered. Nobody knew anything about them. It was related to the early phases of the star formation, right?
Right.
But the whole mystery came about, and it took a long time. And there is Jorge Cantó, there is Luis Felipe Rodriguez, and there are many Americans also involved. But it was, the Mexicans played a big role in disentangling the mystery of the Herwig Haro objects.
Now, right, okay, so anytime you have a telescope, it's kind of useless unless you have an instrument that goes with it.
Exactly.
And the instrument that was being used early on was the Schmidt camera, which, for people who don't know, that allows you to photograph at that time a large area of the sky. So
Exactly.
I know a lot of work was done early on with the development of the Schmidt telescope in California by Fred Zwicky, and his goal was to look for supernovae. So was there any of that type of work that went under there where you are?
Yes, I mean, there are other guys, and the other guy that I wanted to mention is Enrique Chavira, who was a gardener at the observatory, and became. Remember Hamason?
Yes.
So we have a gardener who became became the ablest observer, because he knew how to use the Schmidt camera. And we collaborated with Zwicky. Remember that Zwicky wasn't a very nice guy to work with.
Right.
He was a very tough guy, highly critical, and was paranoid that people were always, taking his ideas, taking credit for his ideas and all these things. And the other work that relates us, Wayne, with the Schmidt cameras is the Abel clusters,
Right.
that you and I have studied, Abel, he was allowed to do Zwicky's work under the supervision of Osterbrock, because they say that Zwicky would not allow anybody to work in the field that he was working. So George Abel was given this job to use and operate the Schmidt camera, but the condition was to develop a project of his own. And those are the clusters that you and I have studied with.
Yeah, so he had access to, which was funded by the National Geographic Society,
Exactly.
the Palomar
Exactly.
Observatory Sky Survey, for those who don't know. Now, Omar, when you think about it, it's kind of like the early days of astronomy in some sense, at least at the time era that we're talking about now, let's say in the 40s and 50s and so on. That was the era of really wide field astronomy with the Schmidt telescopes and so on. And then after that, the focus, no pun intended, was sort of to narrow in on specific targets, so that the largest telescopes were looking at things that, like you think of the 5-meter telescope, Palomar Observatory, looking at very specific targets. And now, because of the invention of these large mosaic cameras, that we were kind of at the ground truth of that starting off back in our day. Now I sound like an old person. That these very large mosaic cameras, whether they're on like the Vera Rubin telescope or anywhere else, we're gone back to wide area astronomy again. And then now the focus is on the follow up on interesting targets that that we're going to discover now. So we kind of did the switch around because of the way the technology has evolved, that we're back to looking at large areas of the sky, looking for diamonds in the rough, essentially.
Yes, but there is a new player here. It's the time domain, Wayne. So they can do the surveys every day, mostly. They can cover large portions of the sky every day. Can you imagine the amount of data that we will have access every day? How are we going to process all that data?
It's petabytes.
Terabytes, and it will create a lot of happy astronomers, I'm sure.
Well, here's an inside joke. This data, we got to store it somewhere. So where do we store data today? We store it in the cloud, right?
Right.
So we're gonna have so much data, we'll have to store it on Venus because that has more clouds.
More clouds.
No, but we will have to using artificial intelligence or
Yes.
computer ways to deal with these huge amounts of data that we cannot even imagine. And it's changing. I mean, I'm looking at the future now. I'm 58 years old, and I say, I would have loved to be born later to see what is going ahead now, what looks ahead with these large telescopes and all the things that we will discover. But fortunately, the comprehension doesn't go as fast as the way we gather data. And still, I think we are in this information tsunami, and the tsunami is just, overwhelming us. And still there is some space for thinking and having good ideas. And that's one of the things, Wayne, if you ask me, I mean, like, what have I done? What is exactly what moves me or in astronomy is ideas, basically. I like to discover things. And you and I have discovered a few things, with clusters that like the color magnitude relationship that you and I have worked on. Nobody thought about it. And I look at them and said, why didn't this occur to them before? And it was basically because they never had played with that data. And that's the thing why I see many of my colleagues or your colleagues or our colleagues to try to get into the largest telescope, the fastest telescope, the biggest detector, and blah blah blah, because they would go without thinking and just cherry picking the discoveries. But that's the way. I mean, you were talking. I heard you about the James Webb Space Telescope. What a marvelous story! All the thing. Every day there is a Nature paper published with data from the James Webb. It's as we're changing the textbooks in real time now.
Right.
Yeah, for sure. One of the things that kind of come out of using this kind of approach to astronomy, where you become a data-rich society in that sense, and the theory is trying to catch up to everything. And one clear illustration of that would be this whole thing with the Hubble tension. And we talked about this on a previous podcast, where local measurements of the expansion rate of the universe is giving us a consistently higher number than using a universal measurement such as observations of the cosmic microwave background, the leftover heat from the Big Bang. So there was a paper that just came out today on the AstroPH print server, and it's by Wendy Freeman and Barry Medor.
Oops.
And the paper is describing they're doing another, if you want to call it that, a key project, not with the Hubble Space Telescope, but now with the James Webb Space Telescope. They're looking at using Cepheid stars and nearby galaxies to calibrate that distance scale. And they published results on one galaxy, which is the paper I mentioned. And in it, they conclude, of course, you can't say anything based on a sample size of one, of course. You need a lot more galaxies than that, so we don't know what effect it's going to have on the measure of the expansion rate. But what they're saying is the aperture that they measured Cepheid stars with the Hubble Space Telescope, when they look at the same stars with the James Webb Space Telescope, they don't see one star, they see like a number of stars. So when using when using the Hubble, you thought you were looking at just the Cepheid star. No, there could have been several unseen companions that were too close to that Cepheid star to be resolved. But with the James Webb Space Telescope, you have higher resolution, and therefore they can see separate stars where normally they thought it was only one. And the effect of that for this one galaxy is that the scatter and the relationship, the period luminosity relationship of the Cepheid stars for that galaxy has been reduced by a factor of 2. So that's it. What is the implication of that for if you had 30 or 40 or 50 galaxies trying to measure independently their distance? And so we don't know yet, right? This is only on the one galaxy, but it's very interesting to realize that just by changing your instrument now, higher resolution obviously, that is affecting a lot of things downstream, and ultimately, the expansion rate of the universe could be tied into all this.
Wow. But they should be like low mass stars then, because the resolution is not greater. The HST had the best resolution, still has. But they were like, if they see all these companions, it should be low mass stars.
Well,
it can be seen in the optical.
Now, remember, it depends on the wavelength, right? So James Webb can see into the
near infrared.
Yeah, but it can see also in the red side of the optical. That's the shortest wavelengths. But at those wavelengths, because the aperture is so much larger, the James Webb, the resolution is actually a lot better than the Hubble Space Telescope.
Okay, so at the near the red wavelengths that it can see, it's better, whereas at the mid infrared it would be
worse. So HST would have NICMOS. That's the only way you could have seen way out into the infrared, right?
Yes.
And so there you're comparing a little bit apples and oranges. So what you do you compare it to Spitzer. But James Webb is superior to Spitzer because the aperture size is like 6.5 meters compared to like 0.9 meters on the Spitzer, right? Or something, right?
0.8 meters.
Yeah.
It's a tiny telescope.
Yes.
But they revolutionized the field.
Oh, it did such great work.
That's why I find it, at first when you hear about the Hubble tension, and we also talked about this idea during a previous podcast.
I understand, yes.
It's like the large-scale structures all around us. We're within that, obviously. And near us is the local void, an underdense region. So if you have an underdense region, that would locally give rise to a little bit faster expansion rate because the density of matter is less on average in some representative volume of space. But with measuring the cosmic microwave background, you're observing over huge scales, and all of those density fluctuations get averaged out. And so naively, I would think that the lower value of the Hubble constant, 68 roughly, compared to 72, 73, 74, 75, depending on who you're talking to, I would think that the more larger scale you're looking at, like with the CMB, would provide a more accurate measurement of the overall expansion rate of the universe, rather than a more localized method that is affected maybe by the fluctuations of large-scale structure.
And you've made him think.
That's
It's very interesting. So you think it will go higher then? It will go to 70, with this correction now.
Well, locally we're being affected by the underdense region, so that will give us a higher value for the expansion rate.
Okay.
But yeah, but using a CMB, you're looking over the observable universe, which means you're averaging over all like thousands and thousands of voids and filaments and all that large scale structure. So all of those fluctuations kind of average out, and you're not affected. Yeah.
Yes, the problem with the Hubble constant is horrible. And you remember, I mean, perhaps you were not there when Scott Remain told us that don't go into the Hubble constant business. Do it when you get a tenure.
Do it when you're emeritus and can use do whatever you want, right?
Right, because it's coarse. I mean, the field, I mean, you got all this time and all these players. Wendy Friedman and Barry Mador is one of the teams, it's got more success using HST and all these things. But remember, I was in 2001, I was at Carnegie Observatories. I went there with a Fulbright scholarship from the Department of the States of America, United States of America. And there were, Sandage was living still. And Wendy Friedman was there, and they didn't talk. Sandage was still fixed on the value of 50 kilometers per second per megaparsec for the Hubble constant. And Wendy would be like 70 around that time. And then it changed, and now the tension. What is the value for taken from the CMB, Wayne?
So it's on the order, so it's about 68 kilometers per second per megaparsec. And here's the amazing thing now, Omar. We've gone from a point, let's say in the early 80s, when de Vaucouleurs was still alive, Gerard de Vaucouleurs, where him and his group was advocating 100 kilometers per second per megaparsec, and Sandage and Tamon and stuff are all advocating 50 kilometers per second per megaparsec. So they're different by a factor of 2. So people who didn't want to get into that split the middle, the difference, right? 75.
75.
Well, it turns out that's about what the value is. It's close to it what we think it is today. But here's the amazing part. We've gone from the early 80s to now 2023, where now we think, at least, that the uncertainties, both random and systematic, are so small on these values now that a value of 68 compared to a value of 73, 74, 75 is more than 5 sigma away from each other.
And that's what the problem is.
And that's what I'm wondering, if we really have a good handle on the systematic uncertainties of our measurements.
I don't think we do.
And that
I don't think we do. Yes, because we haven't understood the Cepheid stars, and they have differences, the metallicity and all the things. And people think that they can account for all these corrections, and basically, at one point, Wayne, all the value of what you're generating is in the corrections. And probably that's one of the big problems we have now. So that's why people should, I would not give them Wendy and Barry more time to do it. I would say, welcome some new guys, new kids in the block using a different distance indicator and do the problem all over again. I would say that.
Well, theorists, of course, jump on this, and what this seems to be the major emphasis is what they call early dark energy.
Oops.
Yeah, so you go away from the cosmological constant, right, into this new energy field in the universe, right, to try to make it so you get this split of these measurements of the expansion rate of the universe. So it's all this stuff. It's like, how do you even observe that and constrain those measurements, right? So it's really drawing. It's almost as if, I need to publish, so I'm going to invent this idea, and maybe I'll get 300 publications out of it, or at least I will be cited in multiple papers. And so that will increase my prestige, and therefore I'll end up with tenure or something, wherever I'm at.
I want to find out a little bit more about what dark energy is before I start saying, okay, it changed value in the early universe from the current universe.
Yeah. You know what it reminds me of, Omar? It reminds me of the time when they only were detecting 1/3 the number of neutrinos coming from the sun.
Yes.
Right?
And that was because we had the number was right, but we haven't considered the neutrino oscillations.
Yeah.
And that's what I'm saying, Wayne, because we get clouded in our minds thinking of a way of thinking, And we need to change. And that is painful, Wayne. I don't know for you, but in you, Robert, but the change in your mind, it takes time, it takes
Yes.
courage, and it takes, it gives you a sense of insecurity because you think, because I'm 68 now, 58 now, I should know and be sure about everything I said. And then you come to this to this crossroads where you have to change your well, they call it paradigm. Yeah, it's a way of thinking. It's an idea, and that is painful because from being an expert, you're a nobody. And
Right.
I don't know, like when you are like so far in your career that you're willing to become a nobody.
Or you're a has
No.
been. Has been as the slang term is. You had your time. Now it's our time. You need to move on.
You get labeled as a dinosaur.
As a
the
dinosaur,
moniker,
right.
On that.
No,
But
but you should be a dinosaur with grace, actually. You should be a dinosaer who accepts other people's idea and actually help. Because what we do, and in America is a prime example of this. Every, so many years, they reinvent themselves. And everything what was known is thrown away. And it's the same in Canada. They shut down telescopes, they shut down museums and blah, blah, blah. And here in Mexico, we don't get rid. I mean, we keep the elders in our places, right? So we value the opinion of the elderly people. And I think we should respect. I mean, they did. I mean, I like history of astronomy. And I actually see and marvel at the way of thinking and the ideas that they push for. Like there is this guy, Stromgren. We all know about Stromgren. Stromgren, Sears, and all this that.
yeah,
He invented a photometric system that was astrophysically motivated. And he said, I want to reproduce the MK classifications with photometry, measuring light instead of getting an spectrum. And the results that you achieve with that photometric systems are so great. And it was because he put a lot of thinking into developing the set of filters that was needed. It only works within a range of types. I mean, like from F to G's or A to G's, more or less. But it works fine. And you can work extensions and things like that. But that is an old idea that nowadays, we're having all these computers and all those things. We don't think much. We just go like I have 1 million stars, right? I write a paper with 2 stars, and you should feel shameful. But, I have 1 million observed with such and such survey, and blah, blah, blah. But if you don't have a good idea, you'll be producing garbage. I mean, you have to think about it.
Right.
Or you're observing with the largest telescope. Well, if your brain is about the same size, you will be taking advantage of that big telescope. And I think we should, reach the middle ground. As I said, I mean, you tend to dominate and all these things. Okay, you should go and tell them, give us a chance. I mean, you work here. But we should combine the old and the new in order to, get more enlightenment. That's what I think. But, the funding agencies don't like that. They say,
No, they want the new, the bright,
course,
the bright and shiny.
Right.
Right.
But then we reinvent things. And you remember these red spirals that were discovered with the cosmic zoo and all these things?
yeah,
You remember them?
yeah.
Well, there was this guy in Toronto, Sidney Vandenberg, who called them anemic
Yeah,
spirals. What is the difference?
that's
Anemic
right.
because it didn't have that much star formation. It didn't have that much H1. It's a paper written with the David Dunlop Observatory, observations from outside Toronto.
Mm-hmm.
And then, you had a big computer, you do, how do you call it, public science, or what is it called? Like
Citizen science. Yeah.
citizen science. And you rediscover the red spirals. Come on, guys, give me a break.
Now, careful, I know some of the people that were involved in the citizen science project.
I wait for them here in Mexico. Let them come.
I was going to say a joke, but I better not.
Yeah.
But, So the way, I mean, that's kind of the future, right? Like for small telescopes, you remember in the early 90s, there's a big push to start closing down the 1, the 2 meter telescopes and so on. In fact, we did our PhD thesis on a 1 meter sized telescope, right?
Of course, like,
And then,
and a large CCD.
right, and then after that, you know, telescopes became important, even the 2 meter class telescope when you're looking for like radial velocity measurements, exoplanets and stuff. Now look at the field. So stellar astronomy almost went through a time period where, you know, if you're involved in stellar astronomy, you're kind of in the old crowd, right? Your advisor is an old
Yes.
person that's ready to retire and stuff. Don't go in that field, it's dead, right? Go into galaxies and cosmology was sort of the motto back then, right, in the mid-90s. But then with the exoplanet explosion, which it really is, I mean, there's a lot more attention now turned on individual stars, right?
Yeah, and we discovered that we didn't know much about stars, right? I mean, it was a revival.
Yeah.
And I'm jumping into that revival, into doing some work with the stars and pulsating stars and all these things, because now the driver is, exoplanets, and it's great. It's a huge thing, but they didn't call the old guys, and the old guys didn't want to talk to the new guys.
I'll talk to him.
Well, there was a paper that just came out recently. I don't know if you've seen it or not. And what it described is, you remember back in the, I guess it would have been early 90s. This was just before I got to Toronto and just within a few months of being there. Carl Camper, observation of Polaris, the nearest Cepheid star to the Earth, right?
Yes.
And he saw that the period was declining. And the prediction was a few years from now, you know, it could be several decades, of course, that essentially that star will no longer be a Cepheid star. It would stop the pulsations. That was a prediction that they made. And this new paper actually uses data over a large period of time, showing you that the pulsation period dwindled down and then it went back up again. And now it's going to dwindle down again. It's starting to go on the other way. So it goes through these long-term sort of fluctuations.
So there's a pulsation to the pulsation.
Yeah, so these long-term fluctuations that normally, I think we lost Omar again.
I think we lost him.
That you would miss unless you had data spread over a huge range of time, many observations over essentially 100 years or more, and this stuff comes to light. And these are Cepheid stars that we think we know the true nature of, that we want to use them to measure the distant scale of the universe. And we don't even understand the nearest Cepheid to us, you know, Polaris. So that makes you wonder, you know, in that sense, right?
It does. And, you know, I go to bat for astronomy that we do know these things, because we do know some of these things. But at the same time, how much do we still not know?
Now, well, I know the argument on the other side would be, if you look at 1,000 of these objects, any little idiosyncrasies that these individual stars would have kind of gets washed out on the average. So that's what you're hoping.
Right.
So then in the mean, at least, that is in the average, you're going to get the right values. You're going to get the right measure to the expansion rate of the universe. But, you know, if you take each object as an individual and drill down deep into their makeup and their very nature, you might come up with a few surprises that we are unaware of today.
Right. And you know, I mean, Type 1a supernova is one of my favorite things to pick out, because how do we know they're the same brightness? How do we know that they always explode with this amount of energy? So, you know, I'm one of those that's a little skeptical of some of our measurements because of this.
Well, that field has been changing a lot since '98, when they were used to measure dark energy. And of course, dark energy's measurement involves not only just the supernova type 1As, but several other different techniques independent of supernovae. But people have been studying more carefully these type of supernovae, and they realize there are different types. They're not just the basic standard few types that we thought of.
Right.
There could be, you know, two objects that are in common envelope type of orbiting around each other in a binary star system type thing, and that has an impact. There are kilonovas, right? Very luminous type of supernovae that go off, right? That you at first would look like a type 1A, but now is a different type altogether. So I think there's a lot more stuff hidden under the rug, right? We like to put a blanket on everything. Omar, you're back with us. Do you remember?
Yes, thank you.
Did you ever see that cartoon? It was Paul Schechter standing with a foot on a blanket, And he was like,
Yes.
the Schechter function, like a blanket on top of the luminosity functions of clusters.
Yeah.
So you hide everything under the rug and don't worry about the details.
He was actually standing on the details.
Yeah, that's right.
Pushing them with his toe and saying, "No, the details should go away." But you mentioned this supernovae business, right?
Yeah.
I mean, like, I've been into meetings and I just get up and tell them, I can standardize even my grandma if I do it, if I want to.
Yeah.
I mean, you get an explosion, you don't know the details, and then you work a correction to standardize. I mean, who tells you that standardization is right? I mean, like, you're comparing a bunch of, this is the details, Wayne. Is the devil that lies in the details. And the details, I cannot trust supernovae as a good indicator. I mean, people will look at me and
They look at you like you've grown a third head,
Yeah, well, they would say, you would never get an NSF grant or anything. Well, I'm not an American. I can say whatever I want. But it's a dead end, I would say, like supernovae. And you mentioned kilonovae, right? Kilonovae is a merger of neutron stars, and you can see the gravitational wave of those things. And then perhaps through there, we can get a good calibration, because you get the gravitational wave when they merge, right?
Right.
And then you can apply the corrections from relativity and all these things. And then you get the luminosity from the star, from the event that you call a kilonova, which is shorter than a supernova. And perhaps through there, I can see an avenue of getting some progress. But for the rest, I think is that you can do as many models as you want. And the standardization, what gives me the chills. And I would say,
Yeah. On that note, I'll comment that, as I was told by one of my professors once upon a time, you can fit a power law to anything. So what he was meaning is you can find an equation that will fit any set of data, probably more than one, if you poke around at it long enough, if you tweak the parameters.
So related to all this, Omar, I wanted to get your opinion on something.
I think he's stuck again.
Okay, so wait till Omar comes back so I make sure that he can hear me. And so this is related to the observation by the James Webb Space Telescope of these galaxies, massive galaxies that were in place very early on, just a few 100 million years after the Big Bang.
Mm-hmm.
And so that's been pointed to as an indication that there's something wrong with our cosmology. So when Omar gets back, I want to get his opinion on what he thinks about this issue. So it's kind of one of those talking points today, right? One of those important subjects that people are interested in trying to figure out what's going on. It's just as much as, the problem, if you like, with the Hubble tension as well, is why do we have these really massive galaxies at high redshift, right? That at early times, there should be time. It takes time for things to form, including galaxies, through gravitational collapse of material. And so why is it then that these things form so early? So Omar, there's been there's an editorial that was just I don't know if you heard about it in the New York Times recently by Adam Frank and Marcelo Glessler, I think is how you pronounce it.
Yes.
Where they basically say we're putting too much emphasis on the standard model of cosmology. We're taking too many things for granted. We got to include dark matter. We don't know what that is. We got to include dark energy. We don't know what that is or where it even comes from. And yet we're seeing this mystery, apparently, of these massive galaxies at a very early time in the history of the universe. So maybe we should have a better look at cosmology. And some experts have scoffed at this because this came out on different podcasts. Where people just jumped on cosmology and said the universe must be a lot older than 13.8 billion years. But now you have essentially cosmologists are saying, wait a minute, maybe we should look at this. So what's your view on all of this?
My view is since 1998, Wayne, I went to a school when I just graduated, when we just saw ourselves in Toronto. I went to a school in Jerusalem, and there was Simon White there. Simon White, the father of cold dark matter. And there was this guy, Weinberg, David Weinberg from Middle East, Midwest University. I don't recall yet. So there were a lot. And they cool. And because of the CD galaxies, Wayne, we cannot form them right now. I mean, they're not. You have to allow a long time for the formation of these gigantic galaxies. So these galaxies are old, and they have, the progenitors of these galaxies, in my view, are old too. So I said and we were looking just, the first results of the deep universe and blah, 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 deep universe of a half. And I said, I think the big galaxies were already there. Everybody looked at me and they took the air and they were all surprised. And they were about to, get in my case, and everybody, including the new students. And there was Simon White who came and said, Omar might be right. There are these big galaxies at high redshift that we cannot explain. And that was it. So I came out as a hero out of there. But I believe that we should rethink about the galaxy formation, Wayne. And I think clusters are the key to learn about these things. Because a new result that I'm about to publish in a month or two, and you're invited to, Wayne, to this venture, is that galaxies in voids are upsizing at low redshift. Take that. Upsizing. They are just forming right now as we found them.
Okay.
And that is going to go against everything that we know, because people believe that it's mass, the main driver, rather than the environment, what drives galaxy formation. No, but now, if you look carefully, you choose your sample right, then you're going to find
I was interested.
Yeah, I remember Jim Peebles, who won the Nobel Prize in physics just a couple of years ago on large-scale structure of the universe. He's a big cosmic microwave background guy.
Right.
At higher redshift is logical.
Yeah, we're losing you, Omar.
Yeah.
But Jim Peebles, who went to the University of Manitoba, so there's a local connection in that sense, not too far away from where we are here. He speculated that we should be looking in voids at the properties of galaxies in the voids, if we potentially could find something interesting.
See,
so
that makes sense.
this is in line with what Omar is talking about. So, yeah, we definitely need to explore all the different environments. We can't just be, looking at one, because you have a very biased view of everything. If you just concentrate either on the high density regions or not, we should be looking at them all. And in some sense, with these large survey that's going on, like with the Vera Rubin telescope, once it's up and running, the LSST project, they'll be surveying the whole southern sky every 3 nights. And so that allows you to look at all these different environments and then just stack that data together. So eventually, you're not only going to see huge areas, swaths of the sky, you're actually going to be seeing a lot deeper, that is, a lot fainter objects. So hopefully, data sets like that will allow us to probe more than what we can today with kind of the limited data compared to what we're going to get. It's the old proverbial drinking from a fire hose thing that's going to occur.
That's a good
So I don't know if you heard my comments about Jim Peebles, how he mentioned just a couple of years ago that we should be looking in the voids and the properties of galaxies.
Yes, no, I'm following him. I went to visit him at the end of 2021.
Okay.
He didn't. I invited him to be part of this project. My project, Wayne. And he said to me that, well, you go on your own. I'm too old to follow you.
Lord have mercy.
But
I went to see him, and guys, Robert too. I mean, now that we met, we should get together. I mean, this is horrible to be interrupted every 5 minutes.
Right.
I went to Princeton to visit Peebles, and I brought him a fine bottle of tequila just for him, the finest I could find in Mexico. I promised the finest tequila for you, the two of you guys, and if we can get together again. And it's been great. It's been great, Wayne. Thank you very much for bringing all these memories, and which I should look at your face, Wayne, because this is not good. Yes.
I'm working on getting that fixed where
Yeah,
we can see each other, while we're doing this.
You're our first guest outside of UND, so
yeah.
All right, good. No, I can arrange my trip to see you guys, and it would be an honor for me
no,
to be with you.
that would be
It would
great for sure.
I would enjoy such a visit.
Yeah,
so,
that would be. Well, I think, Omar, this is a good time to start wrapping up. So first of all,
Yes.
thank you very
Thank-
much for being part of this
Yes.
podcast.
Thank you.
And I just wanted to mention for those of you who are watching that our next podcast will take place next Tuesday, September the 19th, 3 p.m. Central Daylight Time. We always leave you with a quote, Robert.
Yep.
So this quote is by Kep Thorne, and Omar, see if you can guess the book that it came from. I don't know if he's still listening to us or not, but here's the quote. Why are black holes so different from all other objects in the macroscopic universe? Why are they and they alone so elegantly simple? If I knew the answer, it would probably tell me something very deep about the nature of physical laws, but I don't know.
But I don't know.
Wow.
Do you know
Wow.
what book?
The book is in time warps and
Yeah, black holes.
what is it? Time warps? Einstein's outrageous legacy.
Yes,
A great
exactly. That's the book.
That book changed my life, Wayne. I went into black holes research thanks to that book,
Beautiful.
and I can tell you in another time.
Yeah.
Thank you, guys.
Yeah.
It's been a pleasure.
Thank you very much. If you like this podcast, please give us a thumbs up and subscribe to the channel if you haven't already. Thank you very much, and we'll see you next time.
Next time.
Thank you. Bye-bye.